Dear students, today we will discuss the topic thermohaline circulation. As you know, seas and oceans are never still because of deeper forces hidden beneath the water surfaces. Wind-driven ocean currents circulate water horizontally across the ocean surface. There is another much slower but incredibly powerful system working quietly in deep oceans. It is called thermohaline circulation. The word thermohaline comes from two words, thermo meaning temperature and haline meaning salinity or salt content. Cold, salty water becomes denser and sinks, while warmer or less salty water stays near the surface. This simple difference in density puts huge mass of water into motion around the world. In polar regions, surface water becomes very cold and salty as sea ice forms. This dense water then sinks into the deep ocean and slowly begins a long journey along the ocean floor. Far away in warmer regions, lighter water rises to take its place. This rising and sinking creates a massive planet spinning global conveyor belt that links all major oceans. The thermohaline circulation is to Earth what the life support system is to an organism. It moves heat from the equator towards the poles and helps regulate climate. It also carries nutrients from deep water back to the surface, supporting microscopic algae and all the other marine life dependent on them. Without this circulation, much of the ocean would become stagnant and life poor. The lecture is aimed to make the learners understand how it allows it's important for climate oceans and life on Earth. Origin of thermohaline circulation. Surface currents are primarily powered by wind influencing only the upper layer of the ocean and accounting for roughly 10% of the total volume. In contrast, the majority of ocean circulation, about 90%, is driven by currents that operate independently of wind, involving deeper water movement. These currents are formed mainly due to the differences in water density. Seawater density can increase into two ways: when its temperature decreases or when the amount of salt or salinity increases. Out of these two factors, temperature affects density much more than salinity. Change in density caused by salinity are usually small, except in polar regions, where water temperatures are already very low and remain almost constant. The movement of deep ocean water controlled by temperature and salinity. Most of the water involved in this circulation comes from cold, high latitude areas. Show the path of the thermohaline circulation, where blue paths represents deep water currents, while red paths represents surface currents. Thermohaline circulation is often referred to as global conveyor belt, since the movement of warm and cold water functions like an underwater river, transporting water masses across the world oceans. In these regions, surface water becomes extremely cold. At the same time, ice forms, and this ice usually only fresh water. As a result, the surrounding seawater becomes saltier. Because the surface water is now both cold and salty, it becomes very dense and sinks. Once it sinks, it forms a deep ocean current known as thermohaline current. Scientists identify different deep water masses using temperature salinity diagram. Each deep water mass has a unique combination of temperature, salinity and density, which acts like a signature. In polar regions, as heavy surface water sinks, deep water rises to the surface called upwelling. Since both surface and deep water have almost the same temperature, in these cold areas, the water column is called isothermal in TS diagram. A temperature salinity diagram is a tool scientists use to explore how the oceanic temperature, saltiness and density shifts as you go deeper. It helps reveal the vertical layers of water column and the different water masses within it. On the diagram, temperature is shown along y-axis while salinity is plotted on the x-axis. Instead of using the actual temperature measured at depth, oceanographers often use potential temperature, the temperature the water would have if it were lifted to the surface without gaining extra heat from pressure. The diagram also includes lines called isopycnals, which mark points where water has the same density for different combinations of temperature and salinity. After that, you can plot the temperature and salinity values on the diagram. From their intersection point, you can calculate the water density. For instance, a temperature of about 11 degree combined with a salinity of 34.6 PSU leads to a density of 1.0265 grams per centimeter cube. Each significant water mass has its own unique range of temperatures and salinities. So, if a deep water sample falls within the range, it's likely sourced from that water mass. Figures illustrates the typical temperature and salinity ranges for major Atlantic water masses. To explore water masses, oceanographers can measure temperature and salinity at various depths in specific locations. In a highly stratified water column, without mixing, lowering the probe would yield consistent temperature and salinity readings through the first water mass, followed by sudden shift to different but stable reading in the next water mass. If you plot temperature versus salinity on a TS diagram, each water mass would appear as a unique point, but in reality, some mixing occurs within and between the layers. As the probes descend, they encounter water exhibiting properties that fall between those distinctive points. Thus, as depth increases, the points on the TS diagram transition smoothly from one point to another, forming a line that represents the mixing of those two water masses. Figures also showcases the characteristic ranges of temperature and salinity for key Atlantic water masses, including North Atlantic Central Surface Water called NaCSW, Mediterranean Intermediate Water MIW, Antarctic Intermediate Water AAIW, North Atlantic Deep Water NADW, and Antarctic Bottom Water AABW. In the example shown, you can see the NaCSW is found at the surface 0 meter depth. As you go from 0 to about 800 meter, there is a transition from NaCSE into AAIW. Then between about 800 to 2100 meter, AAIW transitions into the NADW layer. Just past 200,000 meters, the deepest water mass is AABW, located at around 4000 meter. You will notice that the transition between NADW and AABW takes place from about 2100 to 4000 meters. However, it is difficult to identify specifically where this vertical flow to the surface is occurring. It is generally believed that it occurs as a gradual uniform upwelling throughout the ocean basins, and that it may be somewhat greater in low latitude regions where the surface temperature are higher. Alternatively, recent research on turbulent mixing rates between deep ocean and surface waters in the Southern Ocean suggests that deep water traveling across rugged bottom topography is a major factor in producing the upwelling that return deep water towards the surface. Conveyor belt circulation. An integrated model combined deep thermohaline circulation and surface currents is shown because the overall circulation pattern resembles a large conveyor belt. The model is called conveyor belt circulation. This is due to, in part, to the difficulty in separating parts of the circulation driven by temperature and salinity from those affected factors such as wind and tidal forces. Beginning in the North Atlantic surface, water carries heat to high latitudes via the Gulf streams. In winter, heat gets transferred from the ocean to the air, which helps warm up northern Europe. As the northern Atlantic cools, the surface water becomes denser and sinks, starting the lower section of this ocean conveyor belt. Here, seawater flows downwards at a rate equal to 100 Amazon river and begins its long journey into the deep basins of all the world oceans. This limb extends all the way to the southern tip of Africa, where it joins the deep water that encircles Antarctica. The deep water that encircles Antarctica includes deep water that descends along the margins of Antarctic continent. The mixture of deep water flows northward into deep Pacific and Indian Ocean basins, where it eventually surfaces and completes the conveyor belt by flowing west and then north again into the North Atlantic Ocean. Dissolved oxygen in deep water. Cold water can dissolve more oxygen than warm water. Thus, deep water circulation brings dense, cold, oxygen enriched water from the surface to deep ocean. During its time in the deep ocean, deep water becomes enriched in nutrients as well due to decomposition of dead organisms and the lack of organisms using nutrient there. In the geological past, warmer water probably constituted a larger portion of deep oceanic waters. As a result, the oceans had a lower oxygen concentration than today, because warm water cannot hold as much oxygen. Moreover, the oxygen content of the oceans has probably fluctuated widely throughout the time. If high latitude surface waters did not sink and eventually return from deep seas to the surface, the distribution of life in the sea would be considerably different. There would be very little life in deep oceans, for instance, because there would be no oxygen for organisms to breathe. The way global circulation works has some significant effects on Earth's environment. It is crucial for moving heat around the planet, bringing warm waters to the poles and cold waters back towards the tropics, which helps keep temperature steady in different regions. This whole conveyor belt system also plays a role in getting oxygen to deep sea ecosystems. That deep water starts as cold surface water that's packed with an oxygen, and when it sinks, it carries that oxygen down where it is needed. Thermohaline circulation spreads this oxygen-rich water throughout the oceans where deep sea creatures use it. The Atlantic bottom water still has a decent amount of oxygen because it retains a lot of what it started with, but as it travels across the oceanic floor, that oxygen gets used up. This is why deep water in the Pacific has much lower oxygen levels compared to the Atlantic, with the Indian Ocean's levels falling somewhere in between. At the same time as this water sinks, it gathers nutrients from decomposed organic matter. Atlantic bottom water is low in nutrients because it hasn't had much time to pick them up, and the original surface water wasn't very nutrient rich either. By the time this bottom water reaches the Indian and Pacific Oceans, it is between soaking up nutrients for centuries, meaning the Pacific has higher nutrient concentrations than the Atlantic. We can actually use the oxygen to nutrient ratio in deep waters to figure out how old a water mass is. Basically, how long it has been since it sank from the surface. Climate changes could seriously disrupt the oceanic conveyor belt by messing with thermohaline circulation. With warming temperatures, especially in the Arctic, we might see the polar ice caps continue to melt, adding a significant amount of fresh water to the surface. This influx of fresh water could create a lighter, less salty surface layer that doesn't sink, which could throw a wrench in the deep circulation and hinder oxygen and nutrient delivery to bottom dwelling organisms. Plus, the sinking of seawater in the Greenland Sea is key to driving the Gulf Stream. As that water sinks, it pulls more surface water northwards. If the polar water stops sinking, the Gulf Stream couldn't weaken, which would mean less heat transported to the poles, potentially cooling down the northern climates. It sounds a bit strange, but global warming might actually lead to colder conditions in Europe, resulting in freezing ports and seas that usually benefit from the warming effects of the Gulf Stream. There is already recent evidence pointing to a decline in Gulf Stream strength, likely a result of the increased melting of Arctic ice. Now, we will discuss the effects of wind and oceanic currents on the thermohaline circulation. Wind and ocean currents have a big hand in managing thermohaline circulation. This involves a massive flow of oceanic water and gets driven by variation in temperature and salinity. Winds that blow across the ocean surface pushes along the top layer of the water. They set up currents which spread heat from the equator out towards the poles. Those surface currents end up shaping the deeper flow too. They point out spots where cold dense water drops down and where warm stuff comes back up. Oceanic currents move salt, nutrients and heat all over the planet. That movement changes water density and ramps up or down the power of thermohaline circulation. The whole setup has shaped Earth's climate over time. Think about ice ages when shifts in these flow led to the fast warming or cooling spells. Scientists dig into the ocean sediments, ice cores and coral records for clues. They want to track how thermohaline circulation shifts in the past. All that info sharpens up climate models. These days, it lets researchers guess better at how coming climate changes might mess with ocean flows and worldwide weather patterns. Now, let us discuss thermohaline circulation and global climate. Thermohaline circulation plays an essential role in shaping global climate patterns by transporting heat and nutrients across the world's ocean. Thermohaline circulation is a large-scale, deep-water oceanic current that plays an important role in controlling Earth's climate. This circulation is driven by sinking of dense water in polar regions, primarily in the North Atlantic, and upwelling of less dense water in other areas. The thermohaline circulation helps distribute heat from the equatorial regions towards the poles, moderating climate conditions in Western Europe and other regions. Thermohaline circulation is closely connected to the meridional overturning circulation, or MOC, which is a major part of the global ocean circulation. The MOC carries warm, salty water northwards near the ocean surface and sends cold, dense water southward at depth. When thermohaline circulation changes, regional climates and weather also change. In the past, change in thermohaline circulation have caused major climate shifts. During the last ice age, a strong weakening of this circulation made the North Atlantic region much colder. Another example is the Younger Dros event about 12,800 years ago, when a large amount of fresh water from melting ice slowed down ocean circulation and led to sudden cooling. Next, we will discuss monitoring and predicting changes in the thermohaline circulation. Thermohaline circulation is the global movement of oceanic water caused by differences in temperature and salt levels, and it plays a very important role in controlling Earth's climate. To study it, scientists use advanced tools like mode array or instruments fixed to the seafloor that give real-time data about the currents, temperature and salinity. Autonomous underwater vehicles can travel across large areas of the ocean to collect detailed information, while satellites provides a global view by measuring sea surfaces, height, temperature and salinity. These tools have greatly improved our ability to monitor thermohaline circulation, but predicting how it will change in the future is still difficult. Climate models often lack the final detail needed to capture the full dynamics of thermohaline circulation, and there is uncertainty about how much fresh water will enter the oceans from melting ice sheets and glaciers. Because of these changes, scientists stress the importance of continued research, expanding monitoring networks, building better climate models, and examining how climate change affects thermohaline circulation will help us understand its role in shaping global climate patterns and improve our ability to predict future changes. Implications of thermohaline circulation changes for future climate. Change in thermohaline circulation can have wide-ranging effects on the Earth's future climate at both regional and global scale. This circulation system helps move heat from the equator to the poles, so any change in the strength can disturb the normal balance of heat on the planet. If thermohaline circulation becomes weaker, less warm water will reach the North Atlantic regions, which may lead to cooler temperatures in the areas such as Western Europe. On the other hand, if the circulation becomes stronger, it could increase warming in certain regions. Changes in this ocean circulation can also affect rainfall patterns by altering how moisture is transported through the atmosphere. Some regions may experience reduced rainfall and droughts, while others may face heavier rainfall and increased flooding. In addition, thermohaline circulation plays a role in stabilizing global climate, so changes in it can increase climate variability and make extremely weather events such as heat waves, cold spells and storms more frequent or intense. Potential impacts of changes in thermohaline circulation on regional and global climate changes its thermohaline circulation can have a significant implications for both regional and global climate. Some potential impacts include regional cooling or warming. A weakening thermohaline circulation may initiate cooling in the northern Atlantic regions, while a strengthening thermohaline circulation could result in warming. Changes in precipitation patterns. Shift in thermohaline circulation can influence regional precipitation patterns, potentially leading to the droughts or floods. Impacts on global climate variability. Changes in thermohaline circulation can affect the variability of global climate patterns, potentially leading to more extreme events. Now, we will discuss consequences for marine ecosystems and global carbon cycle. Impacts on marine productivity. Changes in thermohaline circulation can affect the distribution of nutrients, potentially impact marine productivity and fisheries. Effects on ocean carbon sequestration. Thermohaline circulation plays a role in the ocean ability to sequester carbon. Proxy records and climate model simulations indicate that major components of thermohaline circulation, particularly the Atlantic meridional overturning circulation, have weakened by approximately 15 to 30% since the late 19th to 20th century, potentially reducing deep ocean carbon storage and increasing the fraction of carbon remaining in the atmosphere. Such changes highlight the sensitivity of oceanic carbon sequestration to climate-driven disruptions in large-scale ocean circulations. Changes in thermohaline circulation could impact the ocean carbon sink. This was all about today's lecture. Hope you have enjoyed it. Thank you.